what happens to the reaction? Where R0 is the initial concentration of the reaction. Okay, so initially if we are considering, R will be considered as R0, right? So at time t is equal to 0, that is at initially, what will be the value of R? R will be equal to R0 again, which is the initial concentration. So the total pressure means PT, which will be equal to the contribution of A, B and C, right? PA plus PB plus PC. That will be the total pressure, right? Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 3 of the chapter Chemical Kinetics. So in last session, we discussed about the order and molecularity of the reaction. Yes, what is a zero order reaction, first order reaction and second order reaction we had studied in the last session, as well as how to calculate the molecularity of the reaction. And we also studied the difference between what is order and molecularity. Right, now in today's session, we are going to study about integrated rate equation, which is very important. Okay, so integrated rate equation for a zero order reaction as well as first order reaction we will be studying today. Okay, and the significance of first order rate equation. What is the significance of it? Okay, and the rate constant for first order reaction in gas phase. Okay, so all these we are going to study in this session. So let's begin with the first one, that is integrated rate equation for a zero order reaction. Okay, so already we have studied what is a zero order reaction. The rate of the reaction will be independent of the concentration of the reactant which is taken, right? So zero order reaction is the one in which the rate of the reaction is independent of the molar concentration of the reactant. Okay, so if we are considering a general equation, R giving P, where R is a reactant and P is the product. Okay, rate will be equal to minus dR by dt, okay, or minus d by dt of R. Okay, so this we have studied, it's a differential rate equation, right? Okay, minus d by dt of R. R is the reactant here, which is equal to K into R raised to the power 0, which is a zero order reaction, right? For zero order reaction, we studied that rate is equal to K into R to the power 0. Okay, and we have also studied the equation that rate is equal to minus d by dt of R. Why this minus sign? Because the concentration of the reactants is decreasing. So all this we can link together, right? Rate is equal to K into R to the power 0. Okay, and which is equal to minus dR by dt. So we are taking now these two together here. Okay, and so as any quantity raised to the power 0 is equal to 1, this term becomes 1. Right, so how we can write the equation? Rate will be equal to minus d by dt of concentration of R, which is equal to K into 1. Right, this term becomes 1. Okay, I'll just rearranging this equation. We are not just taking this part and rearranging the equation. That is, dr will be equal to K dt. Okay, as you can see here, minus dr by dt will be equal to K. K into 1 is K itself, right? So I'm just taking this dt to the other side. So the equation becomes dr is equal to minus K dt. So this negative side I have taken into the other side, as well as this dt to the numerator. So the equation becomes dr is equal to minus K dt, which is shown here. Dr is equal to minus K dt. Now we are going to integrate it on both sides. Okay, integrate it here as well as here. We are going to integrate this particular equation. Okay, so after integrating, integral of dr is r itself, right? Integral of dx is x itself. So integral of dr will be r, concentration of r, which will be equal to, okay, so now integral of k, what is k? K is a constant, so we don't have to integrate it, that will be kept outside. Now what happens to integral dt? It will be t. Right, integral dt will be t. So minus kt, and when we are doing integration, there will be a constant as well added. So the constant added here is I. So the equation becomes r is equal to minus kt plus I. That means if we are integrating this particular equation, what happens? dr becomes r. right? And the constant will be taken outside. That means k minus k integral dt, right? Minus k integral dt. So what happens? Minus k t, right? Integral dt becomes t plus a constant I. A constant will be also added, right? So where I is the constant of integration. So I hope till here it is clear. Now we are considering at time 0. That means initially we are going to see. Okay, so at time 0, the concentration of the reactant will be R0, right? R will be equal to R0. At time T is equal to 0, initially the concentration of the reactant will be R0. We are considering this now. So what happens to the reaction where R0 is the initial concentration of the reaction? Okay, so initially if we are considering, R will be considered as R0, right? Because at time T is equal to 0, the concentration will be R0. Now substituting it in equation 1, what happens? R0 will be equal to k into 0 plus 1. That is, in this equation, if we are substituting it, this is the first equation. So at time is equal to 0, R will become R0. Right, R will become R0 and K is a constant, T will become what? 0. At time T is equal to 0 we are considering, right? So what does the equation become? It will become like this, R0 is equal to minus K into 0 at time 0, so 0 plus I. Now this term will become 0, right? Any quantity into 0 is 0. So what is left here? Just I, the constant, right? So R0 will be equal to I. Okay, so I hope till here it is clear. Now, substituting the value of I in the equation 1. Now, we got the value of I. What is the value of I? R0. Now, we are going to substitute R0 in this equation. Okay, that means we are going to change I into R0. We derived now that I is equal to R0, right? So, we are going to put R0 here. So, now how does the equation become? R is equal to minus KT plus R0. So, in the place of I replaced it by R0. So, this is the equation now you obtain. Now, further simplifying the equation, we get the rate constant as we are going to calculate the integrated rate constant, right? Rate equation. So, what are we calculating here? Integrated rate equation. So, just by rearranging this equation. So, it is R is equal to minus KT plus R0, right? So, minus KT if I am bringing to this side, it becomes plus KT. So, how can I rearrange this equation? It will be R0 minus R is equal to KT. Right. This KT is brought here, R is taken there. So, it becomes R0 minus R is equal to KT. Now, how can I write in terms of rate constant? K will be equal to, take this T to the other side, it becomes denominator. So, it will be R0 minus R divided by T, right? So, that is the equation you can see here. By just rearranging it, you get this equation K is equal to R0 minus R by T. So, this is the integrated rate equation for a zero order reaction. Okay, so now comparing equation 2 is this one with equation of a straight line y is equal to mx plus c. Now we are comparing this equation as well as this equation. Okay, this is for a straight line y is equal to mx plus c. If we plot r against t, we get a straight line with slope minus k and intercept equal to r0. That means if you are plotting a graph here, this is the graph for a zero order reaction. Okay, so if you are plotting a graph between r, concentration of reactant, and time, what happens to the concentration? It will decrease, right? So you will get a graph like this. It will be decreasing. Okay. So now if we are comparing these two equations, from here you can see what is m. M is the slope of the graph. And comparing this with this equation, what you can say? Yes, slope is equal to minus k, right? Okay. So slope will be equal to minus k, or else you can write in this form also, k is equal to minus of slope. So from the slope, we can calculate the value of rate constant, right? So this is the importance of this graph. If we plot a graph between concentration of the reactant and time, the slope will give you the negative of the slope, right? Slope is equal to minus k. So the negative of the slope will give you the value of the rate constant, as well as the intercept. Which is the intercept here? C is the intercept. As you can see, what is C here? R0. Okay. So the intercept will give you the initial concentration. So this y-axis value is called as intercept, right? So till here to here. So this is the initial concentration. So the intercept will give you the initial concentration R0 as well. So I hope the graph is also clear. So the integrated rate equation for a zero order reaction is K is equal to R0 minus R by T. R0 is initial concentration. R is concentration at time T divided by T. Okay. And the graph plotted between concentration R and time will give a graph like this, from which we can calculate the slope, which will give you minus of the rate constant value, and the intercept will be R0. So the slope will be equal to minus K and intercept will be equal to R0. So these two quantities we can obtain from the graph between concentration versus time. So I hope it is clear. Now moving on to the integrated rate equation for a first order reaction. Okay, so in first order reaction we have already studied the rate of the reaction will be directly proportional to the molar concentration of the reactant, right? So in first order reaction, the rate of the reaction is proportional to the first power of the concentration of the reactant. So again, if we are considering the general equation, R giving P, R is the reactant, P is the product, then how can we write the rate of this equation? Rate of a first order reaction is rate is equal to K into R to the power 1. R to the power 1 means it is R itself, right? Which is equal to minus dr by dt. Again, rate can be written in this form as well. That is minus d by dt of R. So that is written over here. Rate is equal to minus dr by dt, which is equal to K into R to the power 1, which is actually equal to K into R, right? Okay, so now we are just considering only this part, that is dr by dt will be equal to K dt. Okay, so now we are just considering this part, so we can write the equation as minus d by dt of R will be equal to K R. Okay, so now what we are going to do is this, in this particular equation, this equation you can see, we are bringing the concentration terms together. That means dr is here, we are bringing the R to this side. So the concentration terms will be in the same side. And what do? The dt will be taken to the other side. Okay, so that is what you can see. So once it is done, how does the equation becomes? Minus dr by R is equal to K dt, or else we can also write it as just take the negative to the other side. The equation becomes dr by R will be equal to minus K dt, right? So this is how the equation will become now. Now we are going to integrate this equation on both sides. Okay, now that equation we are going to integrate on both sides. So integral of dr by R will be equal to ln R, right? Ln R, and integral of K dt will be, again we have done it in the previous one also. K is a constant, so minus K will be kept outside. Integral of dt is T plus a constant of integration as well. So the equation becomes ln R is equal to minus KT plus I. Okay, so I hope it is clear. We are integrating this equation, and from here we will get this particular equation. Okay, so where I is the constant of integration. Now again we are going to consider for time is equal to 0. So at time t is equal to 0, that is at initially, what will be the value of R? R will be equal to R0 again, which is the initial concentration. Now we are going to substitute that value into the first equation. So the equation becomes ln R0. Yes, this equation becomes ln R will become R0, right? Ln R0 is equal to minus KT. Now this t will be 0, right? For time t is equal to 0 we are calculating. So the equation becomes ln R0 is equal to minus K into 0 plus I. So this term becomes 0. So our constant of integration I will be now equal to ln R0, right? Now we are going to substitute this I value in this first equation. Okay, so this I value now we obtained it as ln R0. So now we are going to substitute here. How does the equation become? Ln R will be equal to minus KT plus ln 0, right? So substituting we get ln R is equal to minus KT plus ln R0. Okay, so now we are just rearranging the equation. This KT is taken here. So KT will be equal to ln R0 minus ln R. Okay, just rearranging it. ln R0 minus ln R. So ln R0 minus ln R is equal to KT. So this is the equation. Now what is this ln A minus ln B? It is in the form ln A minus ln B. What is ln A minus ln B? This is ln A minus ln B, which is equal to ln A by B, right? ln A by B. So how we can rewrite this equation? ln R0 minus R will be ln R0 divided by R, which will be equal to KT. Right. So in this form we'll get. Now we can just write it in terms of the K. What do we do? Yes, K will be kept here. T we can bring it to the other side. So the equation becomes 1 by T. It is T here. So when we take it to the other side, it becomes 1 by T. 1 by T ln R0 by R will be equal to K. Right. So that is the equation which is written here. K is equal to 1 by T ln R0 by R. So now if we have to convert this ln into log, we have to multiply the equation by 2.303. So we can also write it in the terms of log. The equation becomes K is equal to 2.303 by T. Okay. So now instead of 1, it will become 2.303. That's it. So 2.303 by T log R0 by R. So this is in ln terms, this is in log terms. So in log terms, you have to multiply it by 2.303. Okay. So this is the integrated rate equation for a first order reaction. So I hope it is also clear. Now we are going to study about the significance of the first order integrated rate equation. Okay. So let's see the first point. Consider ln R is equal to minus KT plus ln 0. So we are going to consider this equation. We have already studied this now. Now we are considering this equation. Now comparing this equation with y is equal to mx plus c. Again we are going to compare it with the straight line equation. So now comparing from this we can see what is y here, ln R. What is m? M is the slope, right? M will be equal to minus k, right? And c will be the intercept, which is equal to ln R0. Okay. So if we plot graph between ln R versus time, we get a straight line with slope is equal to minus k and intercept will be ln R0. So just by comparing these two equations itself, we can identify this. Now let's see the graph. If we plot the graph between ln R versus time, ln R versus time, we get a graph in this form, in which the slope will give you the minus of the rate constant. Okay, again slope will be equal to minus k and the intercept, and this intercept will be ln R0. Okay, so I hope the difference between the graph in zero order and first order reaction is clear for you. Now there is one more possibility. The first order rate equation, if we are considering this particular equation in the log form, okay, 2.303 by T log R0 by R. So now I am just rearranging this equation. Log R0 by R will be equal to KT by 2.303. That means I am just keeping this particular term there. So it becomes log R0 by R. Just keeping this term here. Now all the other things I am taking to other side. So T is in the denominator. This comes to the numerator. And this is in the numerator. This will come to the denominator. So this will be equal to KT by 2.303. Okay. So I hope it is clear. Now again we are going to compare this equation also with y is equal to mx plus c. Okay. So now what is y here? Log R0 by R. Now what is the slope here? Okay, and what is x here? X will be time. X is the time here. So what will be m? M will be k by 2.303. This much portion will be the m. Okay, and the constant c. So this much will be the slope value. So now let's plot the graph between log R0 by R. It's not ln, log R0 by R versus time. You'll get a graph like this, in which the slope will be equal to k by 2.303. So I hope the significance of this graph is clear. So if we plot a graph between LNR versus time, you will get a negative slope in which the slope will be equal to minus k and the intercept will be ln r0. Now if you are plotting a graph between log r0 by r versus time, you will get a graph like this in which the slope is k by 2.303. Okay, it is in log form, so k by 2.303. So I hope the graph is also clear. So now the next one, now we are going to consider the rate equation at two different times, t1 and t2. So at time t1, the same equation we have discussed before, ln r1 will be equal to minus k t1 plus ln r0. ln r0 is the initial concentration, so it doesn't change even if it is t1 or t2. So ln r1 will be equal to minus k t1 plus ln r0. Now we are going to consider it for time t2. So the equation becomes ln r2 will be equal to minus k t2 plus ln r0. Okay. So r1 and r2 are the concentration of the reactants at time t1 and t2. Okay. And r0 will be the initial concentration. So now what we are going to do? We are going to subtract equation 2 from equation 1. So the equation becomes ln r1. We are going to subtract these two equations. ln r1 minus ln r2. Okay, ln r1 minus ln r2. Now we are going to the RHS, which will be equal to what we will do, minus kt1 plus ln r0 minus kt2 plus ln r0. So you can see ln r0 is common here. So this will get cancelled. Alright, so the equation becomes minus kt1 minus of minus kt2. It is minus kt2 here. So 2 minus will be there. Okay, so minus into minus is plus. So the equation becomes k into c. This is minus kt1 plus kt2. Right? Minus into minus is plus. So minus kt1 plus kt2. So k is common in both. So I can write it as k into t2 minus t1. Right? It is t2 here and it is minus t1 here. So I can write the equation as k into t2 minus t1. So as you can see, this is the equation written here. So again, we have studied before what is ln A minus ln B. It is ln A by B. So the equation becomes ln R1 by ln R2 is equal to k into T2 minus T1. Okay. So now we have to get it in the terms of k. So just rearranging this equation, this T2 minus T1 term will come to the other side. So it will become 1 by T2 minus T1. So k will be equal to 1 by T2 minus T1 ln R1 by R2. Okay. So this is in the terms of ln. Now if you have to convert it into log, multiply it by 2.303. So the equation becomes 2.303 by T2 minus T1 log R1 by R2. Okay. So this equation is also important if you have the concentration of the reactants at time T1 and T2. So you can substitute R1 and R2 here, T2 and T1 here. You will get the rate constant. Okay. So I hope this is also clear. So this is the significance of first order reaction. So I hope it is clear. Now moving on to the last one, that is rate constant for first order gas phase reaction. So if the reactants and products that we are taking, it is in gaseous phase, there is a small change. So let's see, let's consider this particular reaction. A is the reactant here. A is giving B plus C. So B and C are the products, A is the reactants. All of them are in the gaseous phase. So let Pi be the initial pressure of A and Pt be the total pressure at time t. Okay. So integrated rate equation for such a reaction can be derived as, let us see. So the total pressure means Pt, which will be equal to the contribution of A, B and C. Right, PA plus PB plus PC. That will be the total pressure, right? Okay, where PA, PB and PC are the partial pressures of A, B and C. So the total pressure will be equal to the partial pressure of A plus B plus C. Okay, so I hope it is clear. Now if X ATM, if X is the pressure, decrease in pressure of A. Okay, so after time t, what happens to the pressure of A? It will decrease. Now by how much it is decreasing, we are considering it is decreasing by X. Okay, and 1 mole of each of B and C is being formed. Okay, so the increase in pressure of B and C will be also X ATM each. So let us understand this using this equation. So just now we studied A is giving B plus C. So initially the pressure of A is Pi. And initially, what is the pressure of B and C? It is 0, right? It is not formed yet. So, it is 0. Okay, so now after a time t, we are considering again the pressure of A, B and C. So what happens? The pressure of A has decreased by a value x. So initially it was Pi, it reduced to Pi minus x. So what will be the pressure in B and C? It will be the same, right? It will be x and x. How much has it reduced here? That will be the exactly equal to the pressure formed in B and C. Okay, so now at time t, the pressure at A is Pi minus x. For B, it is x and C, it is x. So now we are going to substitute for the equation of P total. P total, what did we study now? It is PA plus PB plus PC. What is PA? Pi minus x. What is PB? It is x. What is PC? It is again x. So if we open the bracket and expand it, this 2x will get cancelled. So finally, what will be the equation? Pi plus x. Okay. So now we can just rearrange it and write in terms of x. Okay. That is Pt is equal to Pi plus x. So what is x? This is taken to other side. It becomes Pt minus Pi, which is written here. X will be equal to Pt minus Pi. Now we already know that Pa. What is Pa? This is the PA. PA is equal to Pi minus x, and we calculated the value of x here. So substituting that is PA is equal to Pi minus x. Now we are going to substitute this x value here. So the equation becomes Pi into Pt minus Pi. The equation becomes like this. So that is what is written here. Pi minus Pt minus Pi. So that will be totally equal to 2 Pi minus Pt. Okay, so now we are going to substitute in the integrated rate equation. So what we have already studied, K is equal to 2.303 by T log R0 by R we have studied, right? Now we are going to write it in the terms of pressure. Okay, so K is equal to 2.303 by T log of what was R0 there? Now it will be initial pressure, right? So it will be Pi. Pi divided by Pa. Pa it is at time t and Pi it is at initial concentration. Like R0 and R, it will be Pi and Pa. That is it. So now we are going to substitute Pa value in here. Pa just now we calculated, it is 2 into Pi minus Pt. So K will be equal to 2.303 by T log Pi divided by 2 Pi minus Pt. So this is the equation to be used if all the reactants and products are in gaseous phase. So it is 2.303 by 2 log Pi, which is the initial concentration, divided by 2 into Pi minus Pt. So if the reaction is proceeding at gaseous phase, we have to use this particular equation, that is K is equal to 2.303 log Pi. Pi is the initial pressure divided by 2 into Pi minus Pt. Pt is the total pressure. Okay, so I hope this equation is also clear. So in today's session, we have discussed the integrated rate equation for a zero order reaction and first order reaction, and the significance of first order reaction, the graph of zero order as well as first order reaction, and also in the gaseous phase as well. So I hope it is clear. So in the next session, we are going to discuss half-life of a reaction. Like integrated rate equation, half-life of a reaction is also a very important topic. So that we'll be discussing in the next session. So I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.